Okay, so recording has started. Right. So for this week, this is week 03. And I'm going to teach a new topic. And this topic is on shearing stresses. Right. So let's see what is a shearing stress first. Okay, what is a shearing stress, or what direction is acting on the surface. So over here, so shearing stress or shear stress are acting parallel to the surface. Okay, so they're acting parallel to the surface. So now if we happen to have a cantilever beam, so I'm going to sketch out a cantilever beam. So this is our beam, right? So this is where it's built in. Right? And we're going to have this cantilever beam. There's a load applied over here, right? So this load is P, okay? And then this cantilever beam, for explanation purposes, I'm going to divide this beam into layers, okay? I'm going to divide them into layers. Or a beam over here, or another way of explaining this, you have a beam, and this beam is made out of layers, okay? Then we're going to sketch out our transformation. So this is X, this is Y, and this is rotation about Z. So we know that the beam were bent, yes, right? Because we have a bending moment, right? So we have a bending moment. This bending moment is induced by P multiplied by a certain length L over here, right? So there's two modes that you will fail. Okay, so two modes of failure. So one is due to the normal stress induced by the bending moment. So the bending moment, so over here, the moment over here is equal to P times by L. Okay. And the next one is due to the shearing stress. Induced by P, okay, which is also known as the shear force. Okay. So over here, if let's say we have a point over here, point A, all right, and then we have point B, right? So if we were to write this out, okay, so if we were to construct the free body diagram, right, if we were to construct the free body diagram on this beam, right, so this is our free body diagram. So we have P over here, right? So we have a reaction over here, and this is AY. And then we have a counter moment and this is moment at point A. Okay, that is our counter moment. So if we were to sketch our shear force diagram, don't worry about all these first, okay? Not don't worry, but I will teach more detail in shear force and bending moment before term test 2. Okay, we'll get more of this. So if you look at the shear force diagram, all right, so what we have down here in terms of shear force diagram, we're going to see this, okay? Then there'll be a straight line across, okay? And then it will come down, okay? So this shear force that we see has a magnitude of P. So this is in terms of V, and this is in terms of X, and up to here is our certain length, which we call L, right? So shear force. And then the next diagram that we can construct is known as the bending moment diagram. So the bending moment diagram will look like this. Okay. So this is X. Okay, over here is L. Now, where is this X? This X is basically, if you look at this diagram over here, at point A, the X is in this direction. Okay, so at point A is X is equal to 0. Okay, based on our diagram. Okay, so now we also have a bending moment diagram. Okay, so we also have a bending moment. I'm going to focus on negative bending. This is because the structure is bent in a set face manner. So this M. So maximum bending moment will be at the fixed end, P multiplied by L, and then this thing will have this trend. Okay, so this is at 0, 0, and this is at a certain L length L. So this is basically our point A. Okay, this is also our point A. So over there is our point B. Right? So what we're going to focus on is on the shear force. Okay, what we're going to focus on for the next 2 weeks is we're going to focus on how the shear force will induce failure on our structure. Okay, we're going to focus. So the formula so for this course, there's only 2 formulas. Okay, so based on the shear force, so you can see over there here the shear force, we call it V, right? So there are 2 terms I want to introduce to you. Okay, so one is known as the shear flow. Right, one is known as shear flow. So shear flow is equal to Q is equal to VT, VQ over I. Okay, VQ over I is where Q is known as the shear flow. Okay, Q is a shear flow, and the units is in Newton per meter. Right, and then V is our corresponding shear force. Q is our first moment of area. Right, so this is in Newton, this is in meter cube, And finally, I is the second moment of area. Okay, so this is meter 4. So if you look at in terms of units, right? If you look in terms of units, so we have shear force is in Newton, right? Q is in meter cube, and then I is in meter 4, right? This will translate to Newton per meter in terms of unit. So this is the first formula that we're going to use. Again, there are only two major formulas. Okay, there are only two major formulas in this topic. And then the next one, okay, so that is shear flow. The next one is shear stress. I better put this in a box so that you know it's important. Right. The other one is in shear stress. So shear stress, tau, is equal to VQ over IT. Right. So the terms are all the same, except I'm going to define tau is known as our shear stress. So this will be in Newton per meter squared. Okay. And then T is the thickness of the beam. Thickness of the cross-sectional thickness of the beam. Okay, sorry, cross-sectional thickness. Okay, cross-section thickness of the beam. And this will be in meter. So if you look at units wise, right? So again, we have Newton, we have meter cube, then we have meter 4, and then we have meter. So this translates to Newton per meter squared. Okay, so this is also equal to Pascal. So in this course, or in this topic in shearing stress, we only have two formulas. Okay, two key formulas. One is the shear flow, and the other one is the shear stress. Okay. Now, from here, you will ask me, Eugene, if we look at a beam, right, how is the beam going to fail due to shear? Right? It's not so so simple that is like equal to force divided by area. You know, it's a distance. So if you look at this formula over here, the shear stress is VQ over IT. It's very hard to what? Visualize. Yes or no? Right? Unlike normal stress, it's force divided by area. You can understand that. Yeah, force divided by area is very easy. So now we're gonna see how do we induce failure, right, due to the shearing force. So we're going to look at failure. Now, before we go on, did I write this? Yep. So we know that the shear stress, one thing to highlight, the shear stress are acting parallel to the surface. Okay, so to the parallel, not perpendicular, okay, to the surface that we are looking down here. So what we see now, okay, so I'm going to draw the failure by shear force. Okay. So now we are going to look at the deformation pattern. Okay, we're going to look at the deformation pattern. So if we were to look at the deformation pattern, so we know that this is our cantilever beam, right? So because